Okay, let's get going here. So project number 2 is due at noon on Thursday. Thank you for those of you who've already turned yours in early. Please note that I will be in meetings pretty much all day on Thursday, so if you had any last-minute questions regarding the project on Thursday, I will not be available to answer them, unfortunately. Are there any questions before we begin today? Okay, so left off last time on about page 61 in the notes. I'm actually going to jump ahead to 62, then come back to page 61. And we were talking about k-means clustering, where k is the number of clusters that we have to pre-specify before we even do the algorithm itself. And so the purpose of this little subsection then talks about, well, how could we choose k? And there is one numerical way that's available to you to help you choose the value for k. And that's to compute this numerical value that I call w here, which is the within sums of squares divided by the total sums of squares. What does that mean? Well, we've already talked about the within sums of squares in the notes. If I were to put the mathematical value here, it's simply you sum over all the clusters, sum over all the observations, and then sum over all the variables, and then calculate for the rth observation, ith variable in the kth cluster. Calculate that x, or specify that x, I should say, and subtract off then the mean value for variable I in cluster k. Square it. So this is a sum of squares. Within the clusters, this is a sum of squares. So this was defined earlier in the notes. Now, would you prefer a small within sums of squares or a large within sums of squares? Small. And let's take a look at an intuitive reason why, just to make sure it's clear. Let's say simply we have two variables, x1 and x2, and here's my cluster that I'm forming. And let's say I have the choice between two observations to include in the cluster, the purple one or the blue one. In which case, the purple or the blue is going to have the lower within sums of squares? The purple one, because it's closer to the essentially the center. And since we're doing k-means clustering, we're defining the center by the mean. So that's why we want to have a small within sums of squares. So in other words, you can think of it this way, that the smaller the within sums of squares is, the better the clustering is. The better the choice of k is. Now there is a problem though, and that is as k increases, this within sums of squares is always going to go down. And for an intuitive reason. Why? Think of the extreme case where k is equal to the number of observations you have. Well, in that case, in that case, the within sums of squares would be 0. Okay? So, and we'll look at shortly then, well, how do we deal with the fact that this within sums of squares always decreases? Let's get back here to the notes. Okay. So now, the total sums of squares, it basically is a sum of squares, but now assuming that we're not even doing clustering at all. So it's exactly the same formula, but there's one small difference. Notice in this mean here, we don't take into account the cluster. So essentially what we're doing is we're looking at how close is each observation to the overall mean for that variable. for the corresponding variable. So then, would you prefer W to be small or large? Small. Yeah, smaller it is. Essentially, according to this numerical measure, the better the clustering is. Now, let's say if you had a W for, you calculated a W when K was equal to 4. You had a W that for K equal 5. Is this denominator going to change at all? No. So in essence, we could just simply look at the numerator only. But you will often see people look at this, essentially this ratio. This is a number that's always going to be between 0 and 1, and make a decision from that. But I just at least wanted to point out that the denominator here is not necessary, but typically people will still include it. Now this then leads then to what R gives in its output from using the k-means clustering algorithm. What it gives is actually a 1 minus W, not W itself. And so what actually ends up happening is that you have the total sums of squares on the bottom, and then you have on the top total minus within. And R actually calls then the numerator the between sums of squares. So you can see some similarities to what you've seen before, like a Stat 801 course, where you talk about like R-square measures, or when you talk about other measures in ANOVA that correspond to sums of squares. And so, yeah, so you see some similarities here in terms of terminology and the calculations. Now let me go back to then page, actually I'm going to go back to page 60. Actually, we'll go back to page 58. There we go. Okay, page 58. This corresponded to the output from the corresponds to the output with the 4 observation data set, and we had K equal to 2. In the output, you see something that says between underscore SS, between sums of squares, divided by total underscore SS, total sums of squares, and you get 54.4%. So essentially, the clustering algorithm is accounting for 54% of the total variation in the data. Now, in this case, would we want this number to be large or small? Large. Okay, so just be careful. We want W to be small. We want 1 minus W, which what this represents then, to be large. And again, this would be a number between 0 and 1. Now, what would happen if, now remember with this k-means clustering, it is dependent on the result that you get in terms of which observations go into which cluster is dependent upon what the initial seeds are. So what if we actually use a different seed number before we ran k-means clustering, and in this case actually what ends up happening is additional initial seeds are chosen, and this is what we get for then the cluster memberships, meaning observation 1 goes into cluster 1, observation 2 goes into cluster 2, observation 3 goes into cluster 2, and observation 4 goes into cluster 1. Previously, we had observations 1 and 2 in one cluster, and observations 3 and 4 in another cluster. So then to evaluate, well, did we do better with this different result? This is where we can look at this 1 minus W value. You get 44.9%. So which result would you prefer? This new one here or the one that we had previously? The one from previously, because it had a higher 1 minus W. But this shows you, again, that depending upon what the initial seeds are, you can get a different result. And that's why it's important to try to implement this algorithm multiple times and then use the one that gives you the best value. Okay, so then that takes us into page 63. Sorry to be jumping around. So now, how do we make the decision if we're looking at K equal 1, K equal 2, K equal 3, K equal 4, and so on? How do we make a decision of which one is the best? And again, what you could do is, you could do, for example, PCA plots, or plots of the principal component scores, and look at them for a different set of values of K to see which result makes the most sense. You can look at parallel coordinates plots. You can also look at this W measure to help make a decision. And so what you can do is plot the values of W. So what we have here on the y-axis, we have values of W, and they are plotted versus values of K. As I told you, this within sums of squares always decreases as K increases. So we can't necessarily look for the minimum value with respect to the y-axis. Instead, what we do is what's similar to what we did with a scree plot. We look for where do I start seeing a leveling off here in this plot. And you can see this is kind of a judgment call. Another person might have a different answer in the end. And sometimes it's difficult to find where does this plot tend to level off. The reason why we're looking for where this levels off is because what this says is that for larger values of K, after this leveling off occurs, you're not really getting that much of a benefit from increasing K. So why don't we just, in this case, stop at K equal 4 and choose that as the number of clusters. Again, on the y-axis, instead, you could just equivalently plot just the within sums of squares too. Okay, so with this tool and also the various plotting tools that we've looked at, again, parallel coordinate plots, principal component score plots, you can make a judgment. Are there any questions? Now, before we actually apply this then to a real data set, let's talk about another topic, and that is the results from these different cluster seeds. As I just mentioned a few minutes ago, our k-means clustering is dependent upon what we use for the initial cluster seeds. The algorithm that we have is trying to essentially minimize this within sums of squares, but it's not a perfect algorithm. You may not get the overall minimum. So because of that, we need to rerun the k-means clustering for the same k with a number of different initial seeds. And there's a few different ways to do that. The first way is essentially what I had just shown you with the 4-observation data set, and that is simply set a different seed before k-means, run it a few times, and compare the results. The best result overall you could define as the one that gives you the smallest within sums of squares, or the largest 1 minus W. Please note that error that's in the notes. Please change. I think that was originally increase. It should be decrease. Fortunately, the k-means function actually makes it a little bit easier for you, so that typically you're not going to have to implement number 1. And instead, in this second way, is that you can use an argument called nStart in k-means. And that basically says to R, rerun k-means nStart times automatically. So if I say nStart equal 10, what R is going to do is essentially run the k-means algorithm 10 different times using 10 randomly chosen sets of initial seeds. And then it will return to you the best results, which correspond to the smallest W. It will only return that set of results. Okay, so let's take a look at an implementation then with the goblet data set. So what I decided to do was run k-means, starting with k equal 1. Obviously, it doesn't make sense to use k equal 1, but obviously also too, it's a nice place to start for comparative purposes here. Start at k equal 1, go up to k equal 10. Now, why didn't I go larger for my values of k? Well, I only have like 24, 25 observations. Probably 10 clusters is too much. If I ended up choosing, let's say, 10 or 15 clusters, I would probably not even use cluster analysis. Also, what I'm going to do is use n star equal 10. Now, there's not a set rule on how many, what that value should be. Obviously, the larger it is, the better. The smaller it is, the worse. Well, you have to make some kind of choice, and I thought 10 successive runs would be good, especially with the fact that, again, I only have 25 observations. Or is it 24? Something like that. Okay. So to implement, then, this process of trying different values of k, what I did was I wrote a for loop. Now, we saw for loops earlier in this cluster analysis set of notes. And basically what I'm going to do for every k, I'm going to implement this within a for loop and then save the results. So here's my code. The values of k that I'm interested in is 1 to 10. So 1 colon 10 again gives me integers 1, 2, 3 up to 10. I'm going to save my within sums of squares into an object called save.wss. And as a way to initialize this thing this object, I'm essentially going to create a vector that has for now just zeros in it. And the way that I can create that vector, we probably haven't seen before, is just to use then the function called numeric. I want to create a vector of numerical values, and I want 10, this vector to have a length of 10. So I'll just show you real quick. Make sure that this data is in R. So save.wss, you can see, has been initialized to values of 0. Now, I'm going to set a seed so I can reproduce my results if I need it for some reason. Maybe to go back, if I got something strange occurring, I can go back and examine better what happened. And then here's the start of my for loop. I say for values of k, could use a different letter, but it seemed to make sense to use k, in 1 to 10, I want to do the following. The first thing I'm going to do is implement the k-means function just like how we've done before. The x argument corresponds to my data. Notice I'm using standardized values. The number of clusters corresponds again to the centers argument, k. So the first time through the loop, k is equal to 1, so centers is equal to 1. Then I'm going to say n star equal 10 to basically repeat this k-means clustering algorithm 10 times. So essentially what I'm doing is I'm using k-means clustering overall 100 different times. So I'm looking at 10 different values of k, and I have n star equal to 10. Next, what I'm going to do is, and we saw this last time, I'm going to pull my within sums of squares out of the resulting object called clus.means. So that component is called within SS. I'm going to sum it up because basically what this does actually gives you the sum for each cluster. And then put the results into my save vector, the kth element of it. So at k equal 1, this runs. At k equal 2, this is going to do it again. K equal 3 is going to do it again, and so on. So that now, here are all my within sums of squares. Any questions about that for loop there? You can see it runs pretty quick. Okay, now I want to calculate W. And when I was going over my notes last night, I thought, well, let's calculate the total sums of squares a little bit easier. And so what I did was in the notes, I decided to remove that and then replace it simply with clus.means. I'm going to pull out the total sums of squares from that. So in the very last implementation, when k is equal to 10, I'm going to get the total sums of squares. It's going to be put into the clus.means object. And now here I'm just going to pull out. Remember, the total sum of squares doesn't change as a function of k. So that's why I can do this.
Just out of curiosity, where you, the second line of the for loop where you have that sum, isn't there also a variable inside that object that has the sum already?
I don't think so. I mean, let me just double check. Obviously, if it did, it would make it easier. Let me just double check. Yep, you're right. That makes it a little bit easier. Thank you. I was just trying to make our lives more difficult. Excuse me?
What was the point of this? I kind of missed.
Okay. Within my for loop, I sum the values are within the SS object. And within the SS object, what you have is for each cluster what the within sums of squares is. And so you could either sum the elements up that are within there, or you could just take it from this. Okay, so I calculate the total sums of squares, or I get the total sums of squares out, and then simply I create a data frame here, and obviously that is not as well as constructed as well as it should have been. Sorry about that. So this is for k equal 1, 2, 3, down to 10. Here's a simple fix to that. So instead of using k in the data frame, use k.levels. And there's the result. And as you can see, again, as we would expect, this W, which is in the right-hand column, so might even been better to do this. Oops. This W decreases as a function of k. Okay, let's actually look at a graph of that. So I just simply use the plot function as what we've done many times before, so I'm not going to go over the details. And here's a plot. Again, what we're looking for in this plot is where does W start leveling off? And I don't think that this is necessarily a clear-cut case for where you can say that W levels off. I would say, generally speaking, maybe at 4 clusters, maybe at 5 clusters, maybe even at 6 clusters. This is not a perfect. This procedure is not always perfect. But this is what, based from what I see in this plot, I'm thinking 4 or 5 or 6 maybe. So then, well, what do you do? Because eventually you need to decide one value for the number of clusters that you're going to use. And that's where, again, these plots of the principal component scores and the parallel coordinate plots can be helpful. So let's take a look at some. Please note that the small little change in the notes. So what I decided to do here was, well, let's look at the output if I were to use 5 clusters. So I set a seed so I can reproduce the results. I use n start equal 10 once more, and I get the output. So for example, observation 1's in cluster 2, observation 2's in cluster number 5, and so on. And then similar to what we had with the agglomerative clustering methods, I wrote my own function, which you are responsible for understanding how it works and the stuff that's inside of it. I wrote my own function called pca.ca.plot2, which now does the principal component plots to allow us to visualize these clusters. So I run that with the results. Let me just show you the call to the function. So I simply pass in my data set. I pass in my cluster results from using the k-means algorithm, or the k-means function, and then I just simply put a plot title on it. Let me actually go ahead. Let me run this, because I know I've run this a few times. I want to make sure I'm showing you the right ones, right results. Let's see here. Okay. Let me come back over here. I'm going to make this a little bit bigger. So with 5 clusters, this is what we get. So on the left-hand side, principal component number 1 versus principal component number 2. Here are my clusters, 4, 5, and 17, 23, observations 23 and 24. Notice here, 3, 16, and 18 are now together in one cluster. Then we have this red cluster up here, and we have a blue cluster down there, light blue. So that's what this is saying. If we add also now the third principal component by looking at then the bubble plot, you can again see something very similar. One thing that kind of concerns me is that notice how in this lower left-hand corner cluster we see both the blue and the red bubbles being joined together. What that means is that we have some positive and some negative third principal component scores in the same cluster. It's not necessarily anything wrong with it, but again, this is showing that there are some differences amongst the observations. And again, cluster analysis, we're looking for observations that are similar to one another. We want to group those together. Let's take a look at some 3D plots. Okay. Oops. So we can see here, if you follow where my mouse is, here's 23 and 24 in the green. We're using the same colors that was in this plot over there. We can also see 4, 5, and 17. That, those choices make sense for the clusters. Let's see now. So we have the darker blue here corresponds to 3, 16, 18. And you can see that they are a little bit separated from the other observations, so maybe that does make sense to have a separate cluster. It's just my one concern then is that if you take a look at the light blue here, corresponds to what's in the lower left-hand corner, and you can see some light blue now that's down below, and it's kind of almost mixed in with the red. So it's kind of somewhat questionable, I think, that necessarily that those points should be distinct from one another's in those clusters. So maybe 5 clusters is too much. Let's take a look at a parallel coordinate plot. This is on page 69. I'm using the same colors here as what was in the previous plots. And so if we take a look at the black lines, first of all, those correspond to 4, 5, and 17. And again, we see why it makes sense for those observations to be separated from the rest. They have large W4 and W5 values in comparison to the other observations. Observations 23 and 24, if you remember, are in the green. And again, there's distinctions between those observations and the others. They have large W1 and W2 values, just like the black, but now they have lower W4 and W5 values. So that's why they're distinct. That's why they're different. But what we also see here is that there's a kind of an overlap between the red and the blue. And again, just to put this in perspective, that corresponds to what we were seeing in the lower left-hand corner here between the red and the, I should say, the light blue. That, you know, maybe it's not as clear-cut that indeed that those are separate clusters. And we see that to some respect in this plot here. You know, you see a lot of overlap. There are some cases where, you know, it looks like maybe the red is higher for W1 and W5. That maybe that's what makes it distinct. Maybe that's what made the algorithm separate those out into separate clusters. Or maybe, you know, instead, 5 clusters is too much. Indeed, and maybe we should have just had 4. Let me make sure I'm covering everything here. So again, in these kinds of situations too, if let's say this is the, if you are satisfied with the results from this clustering algorithm, you know, this is where now you would want to try to interpret what these clusters represent. And that's what I have shown on page 70 in the notes. And I kind of said that in class here. But you know, it's always important to try to interpret what the clusters represent in the context of the original problem. That's why you're doing the cluster analysis in the first place. It's not just an exercise. On page 69, I actually I give you a question. Well, how could you plot the cluster means? You know, this is, after all, k-means clustering. How could you plot the cluster means on, let's say, one of these plots here? Well, obviously, you would first need to find the cluster means. How would you find the cluster means? Yeah, I think the k-means function, I wasn't thinking of that, but I do think the k-means function gives that information to you. Just go through that. Yeah. So it gives it to you right there. And I would assume, yep, the center's argument would give you then the cluster means. Okay, now that you have the cluster means, we need to translate it now essentially to the parallel coordinate system. I'm sorry, not the parallel coordinate system, the principal component system. How would you do that? Yeah, use the predict function to find the principal component scores. And so what you could actually do is visualize where the cluster means in the principal component axis system that we have here. You can actually visualize it on one of these plots. So on page 70, then I say, well, you know, as I've already kind of said out loud, you know, I'm not necessarily satisfied with with 5 clusters, and so it will be good to examine other number of clusters to make a decision of, well, maybe something else is better. And so what I have here said, examine some different number of clusters on your own. I have the code set up in the program already to help you do that. Just for illustrative purposes, let's look at 3 clusters. Let's see if we think that this is better. Okay, so with 3 clusters, this is what we get. 4, 5, and 17 again are together, but now notice where 18 is. 23 and 24 together as before, but now notice 10 and 12. 10 and 22 are there. And now we have in the lower left-hand corner all the observations kind of grouped together. So what do you think? Do you think this is better? Well, I was dissatisfied with more with this. Now we got to be careful here. With goblet data, we said probably two principal components is probably enough. That third principal component is not really contributing that much information. So perhaps, I shouldn't be so critical about the fact that there are some positive and negative third principal components that are in the same cluster. Perhaps I shouldn't be that critical of it. But that's where my problem was. I would have rather seen, maybe something that looked like this. That if we're going to, divide these up in the lower left-hand side, let's divide them up like this. Now, that's if we are going to divide it up. Now with 3 clusters, we don't have to divide it up. And so to some respect, I'm more satisfied with this aspect. I'm not necessarily sure about, let's say 10 and 22 with those guys up there. And maybe, what do we do with 18? But you see us going through this, you can see that there's more than one justifiable answer. There's not one perfect answer. Okay? Remember where cluster analysis is used. It's used for exploratory data analysis. We are trying to find partitions or groupings of like observations. And in real data sets, what's often going to happen is that there's not going to be a clear-cut distinction for some observations. Let's take a look at, let me just give me a second here. Let me actually run it. So here's the 3D plot now with the 3 clusters. And focus on the black ones. This is 23 and 24 again. Now look at where those other 2 observations, which were 22 and 10, look where they appear. They seem to be kind of far apart. And so that's where, again, some of my concern was with respect to 10 and 22. Does it really make sense to put them in there with 23 and 24? Or does it make sense to put it in the green? Well, you can see that there is some distance there too. Here's then the parallel coordinate plot. And you can see, for example, if you look at W2, focus on the black cluster. This is, here's 23, look at my mouse, here's 24, but now here is, let's see now, let me actually go over here. Oops. But here are the other 2 observations that was somewhat questionable. Do we group them with 23 and 24? You can see that there are some differences. And in fact, they are kind of overlapping where the green is. Perhaps as a student, you would always like to have clear-cut answers. You know definitely what the correct answer is. And as you can see here, there could be more than one correct answer. You just need to be able to justify your results. I kind of, went through that. Let's see. Okay. So that concludes then cluster analysis. Any questions? Okay, so to help us see where we are in this course, if you remember the first day of class, I basically broke up the course into 4 different overall sections, for the lack of a better name. We had background material, then we had summarizing data, which maybe perhaps a better name would have been exploratory data analysis. And we have just now finished this section 2. Now we're going to go into section 3, which I call prediction. And what this basically means is this, that what I would like to do is to be able to predict the correct grouping, the correct population, the correct classification for an observation. Let's relate this to the place-kicking data set that we saw earlier in the semester. We had about 1,400 and some observations of place kicks that happened during a particular NFL season. And for each observation, we measured a number of different variables, such as distance, was it windy or not, was there pressure or not, and so on. We measured a number of variables. We also measured, well, was the place kick a success or not? So essentially, we have 2 populations of observations, you could say. Success population, a failure population. Or equivalently, you could say, I have 2 different groupings for my observations, success or failure, or I have 2 different classifications for my observations, success or failure. I'm purposely using the different terminology because different people will use the different terminology outside this class, so that's why you need to get used to it. And so we want to be able to predict, given a certain distance, given a certain wind conditions, given a certain pressure conditions, is this place kick going to be a success or is it going to be a failure? That's going to be our ultimate goal in this prediction section. And we're going to look at essentially 4 different main ways to do this. This is actually an area where there's a lot of research going on, and there's many different methods that are being developed out there still. We're going to look at some classical methods, and then we're going to also look at some newer methods in our class. The first set of methods is what's the most classical, I would say. It's called, fall under the heading of what's called discriminant analysis. Discriminant analysis starts from the perspective of you have multiple populations, like a success population and a failure population, and let's say the variables such as distance, pressure, wind conditions, those variables come from a multivariate normal distribution. So we will have a multivariate normal distribution underlying assumption for discriminant analysis. We will no longer have that distribution assumption for the other 3 methods that we are going to look at. Even though that there is a multivariate normal distribution assumption, this discriminant analysis is often very robust to non-normality, meaning that it still works pretty good, even if you don't have your assumptions fully satisfied. To help motivate the problem further and to give us some examples of where discriminant analysis is used, let's take a look at some examples. So again, we have this place-kicking data set. I've already described it to you. But the ultimate goal then with this place-kicking data set then would be is, put yourself in the shoes of Bo Pelini. He needs help right now. And let's say he's faced with a situation of should he go for a field goal or not? Well, based upon some discriminant analysis results, he can then determine this place kick, or this field goal, if I attempt it, is very likely to be a success or is very likely to be a failure. And based upon that, he can make a judgment of what to do. But the key was, in order to make do this discriminant analysis, to come up with what's often referred to in discriminant analysis, a classification rule. He needed to collect a sample, and in the sample he needed to have the variables such as distance, pressure, wind speed, and so on. But he also needed to know, well, what was the end result for that place kick? Was it a success or failure? But the ultimate goal now is then to use then the result that you got from that data set to apply it to a new situation where you don't know what the result will be. And so you can predict it. Okay. Here's another example. if you've taken my Stat 875 class, you'll be familiar with this data set. This is the wheat kernel data set. We're just going to be looking at it in a different way than what we did in our 875 class. This wheat kernel data set actually comes from a consulting problem that I worked on a number of years ago. And the subject matter researcher that I was working with wanted to come up with an automated way to classify wheat kernels into 3 different populations, 3 different classifications, 3 different groups. A healthy kernel, meaning everything's good with it. A sprout kernel, which basically means, okay, see that sprouted. Or a scab kernel, which basically means is that the kernel has some kind of fungus or disease visible, let's say, on it. Ideally, healthy kernels are the best, and you want to have only healthy kernels. Sprout and scab kernels are not as desirable. They will have lower, let's say, qualities to them when people process then these kernels to make flour. And so it would be nice if one could have some kind of automated process that says, okay, this is a healthy kernel, this is a sprout kernel, this is a scab kernel. And perhaps, let's say pay a farmer a certain amount of money depending upon how many are healthy, how many are sprout, how many are scab. And so to develop this automated method, the researcher developed a way to automatically determine what the density of the kernel is, the hardness of the kernel, the size, the weight, and the moisture content of the kernel. And so he took a sample, about 275 kernels, I believe, put it into this automated system to come up with this information. Also, what the researcher did was he had, let's say, some experts in the field actually physically look at each of those corresponding kernels and determine, is it truly a healthy one? Is it truly a sprout one? Is it truly a scab one? So we know what the correct classification is. What we would like to do now with discriminant analysis, and this is what I actually did with the researcher, was based upon just these measurements here, could I correctly classify? Could I correctly find the populations for these kernels based upon those measurements and using this technique called discriminant analysis? And so you can see an overall then measurement of how good discriminant analysis or any of these other methods that we're going to talk about in this section does, how good it does, or yeah, it does, will be the correct classification percentage. The higher this percentage is, the better the method is. And when we have, as you saw, 4 different methods that we're going to be looking at of how to determine populations, how to determine classifications, you can see the overall best one is going to be the one that gives you the highest percentage of correct classifications. And as you might expect, since we're talking about 4 different methods, not one method always works best in all situations. Let's take a look at one more example. This also comes from an actual problem that I worked on. When I was a graduate student, I spent a summer out at the Idaho National Laboratory. At the time it was called Idaho National Engineering and Environmental Laboratory. They dropped the E's. Now it's just the Idaho National Laboratory. It's a Department of Energy laboratory. And the ultimate goal of the project main project I worked on out there in Idaho Falls, Idaho, was we wanted to determine what was the contents of an unexploded artillery shell. So you can imagine a battlefield situation. You have maybe some unexploded artillery shells laying on the battlefield. Obviously, you want to be careful with them, and you want to determine what's inside of them. Are they a chance empty, or maybe there's mustard gas in them, or maybe some other, obviously non-desirable thing inside of them. And so we wanted to develop ways to determine what was inside it. This is an Army-sponsored project. And my mentor, Larry Blackwood, and an engineer, unfortunately I can't remember his first name, Rodriguez, they put together, they developed some methods to do this. But then when I was there, they wanted to develop some better methods, basically methods that would not, let's say, contact the artillery shell when it's trying to take some kind of measurements to determine what's inside of it. obviously you probably don't want to touch the artillery shell. That might cause explosion. So we wanted to come up with non-contact methods to determine what's inside an artillery shell. And basically what we did, and actually I was involved with the data collection too, which is unusual for a statistician, we basically were bouncing sound waves off of it. And based upon the acoustic spectrum that we got back, that helped us determine what was inside. But since this was the beginning of this research project, of this non-contacting way of determining what's inside the artillery shell, we didn't actually use artillery shells. Instead, we actually used something else as kind of a proxy to see if we can get to work with this easier thing first. If we work for that easier thing, then we're going to try for the harder thing, these artillery shells. So I actually have an object that we collected data on. I was able to keep it as a souvenir. So lucky. And so I spent then my whole summer trying to determine what's inside a Sunny D juice container. Well, juice, perhaps, but we also pour the juice out of some Sunny D juice containers, and we put water inside. We left some that were empty, and we left some, and we actually put sand in some of them. And so you can imagine, the acoustic spectrum when you're, let's say, focusing some sound waves on it, are going to probably be different for sand versus if it was empty. So that's what I spent my summer on. And I will give you some more information about what happened as we go along in this section. So you can see that these discriminant analysis methods and just methods overall that are trying to predict a classification, try to predict a population, are quite important, and they're very used a lot. Please note that these small clarifications are in the notes. So what discriminant analysis does is something similar to what normal linear regression does. You have some explanatory variables or independent variables, and you're trying to predict a response. In normal linear regression, our response, let's call it y, has a normal distribution to it. It's a continuous value. Here instead, essentially our response corresponds to our population or our group. And obviously it's then categorical in nature. Success or failure, for example, with the place-kicking data set. So because of that, then we have to use other statistical methods. We can't just use normal linear regression. This area of prediction for groups, prediction of populations is huge. And again, one could teach a whole course on it. To give you an idea of just how big it is, take a look at the multivariate and the machine learning CRAN task views on the R website. And you'll see all the packages that have been developed just so far to do this kind of stuff. Okay, so now let's talk about then the details of what discriminant analysis does. We're going to start off with the simplest case possible. We have two populations, and we're also going to make some additional assumptions coming up, and then we'll generalize as we go along. So let's suppose that we had two multivariate normal populations. And just to make things easier, I think it's easier, we're going to say population 1 is simply denoted by the Greek letter pi 1, uppercase pi. Population 2 is denoted by pi 2. So pi 1 has a multivariate normal distribution, p variate, meaning p variables to it. It has a mean, mu1. It has a covariance matrix, sigma 1. Population 2, then, multivariate normal, mean 2, sigma 2. And let's say we are concerned about x, which represents a particular item that we have. And it's p variate, p by 1. And using then this information that we have about this item in x, we're going to try to classify it into population 1 or population number 2. Hopefully correctly classify or correctly predict its population. We're going to look at 4 different ways to do this, and they all have equivalencies to them. So you might be thinking, well, why don't I just focus on one instead of talking about 4? The reason why I'm doing 4 is because sometimes you'll hear one person do one way. Sometimes you'll hear another person talk about it a different way. Sometimes you'll have another person talk about it another way. And since this is just kind of due to the nature of our class, that's why I need to talk about all 4 so that you're prepared to deal with them outside of this class. Okay, so the first one is what's called the likelihood rule. And simply what this does is it evaluates the likelihood function for both populations at x. So here's my multivariate normal distribution. And notice how I have x in there. Now we talked about likelihood functions and maximum likelihood estimation for the factor analysis section. And what we talked about is that the larger this likelihood function is, the more plausible, let's say, a set of parameters are, given your data. Well, essentially, my data is x here. So in order to decide, well, which population does x belong to, population 1 or 2, simply evaluate the likelihood functions. If the likelihood function for population 1 is larger at x than it is for population 2, classify x into population 1. Otherwise, population 2. Seems rather simple. It is. Now we're going to talk about the second way to do this. This is often referred to as the linear discriminant rule. And we're going to make one simplification. Suppose you have equal covariance matrices. We'll look at later how you can get around that. But let's suppose that we have equal covariance matrices. If we go back to the likelihood rule, you notice some simplifications then. If sigma 1 was equal to sigma 2, notice the stuff outside of E would be essentially the same. So you could throw that out. Obviously, in both cases we had that E there. Well, you could throw that away. And the only thing that's going to be then different between the two likelihood functions, if sigma 1 is equal to sigma 2, will be the stuff that you see inside of here. So you can play around with it, do some math, and find out then that the likelihood rule then simplifies down to just this. Choose population 1, which will then correspond to the maximum likelihood function. Choose population 1 if a vector B, which is sigma inverse times mu1 minus mu2, times your x, subtract off k, which is another constant based upon your mu's and your sigma. If b prime x minus k is greater than 0, choose population 1. Otherwise, choose population 2. And again, this is just a simplification of the likelihood rule because the covariance matrices are equal. You can go through the math and see that. So that's rule number, let's say, classification rule number 1, or 2, I should say. Rule number 3, or the third way to go about doing this, is what's called the Mahalanobis distance rule. Mahalanobis is a famous statistician, Indian statistician, and please make this, just wanted to make sure it was clear. Suppose again, sigma 1 was equal to sigma 2. Then the likelihood rule, and also then the linear discriminant rule, is equivalent to looking at the problem in this way. Let's calculate a distance that x is to the corresponding population, population 1 or population 2. Now we talked about how to calculate distances between two vectors in the cluster analysis section. If you remember, Euclidean distance was simply, say I have two vectors, x1 and x2. This was Euclidean distance. Instead, what we're going to use is what's called Mahalanobis distance. And you can see some similarities to it. Now, what I'm doing is I'm calculating what's the distance that x is to the center, essentially, of a population. Population 1 or population 2. So x minus mu I. But I am also going to take into account the variability in the data, and so that's why you have a sigma inverse in there. What does this simplify down to if p was equal to 1? Meaning I only had one variable. You're going to have something in the numerator, you're going to have something in the denominator. What goes in the numerator? Well, think about that. So we have this distance. And so you might think then, well, the smallest distance that x is to one of these populations then corresponds to which population I should classify x into. So if I have two distances, let's call it d1, the distance that x is to population 1, d2, the distance that x is to population 2. If d1 is less than d2, well, then classify x into population 1. Otherwise, population 2. And that's how it works. It's just, again, a little bit of a different way to think about this, but it's still all equivalent, mathematically equivalent. And so this is just kind of a graph showing what we would do. That, if I have two variables, x1 and x2, and let's say the variances are the same between these two variables, the ellipses there that you see are contours, the same contours for the two multivariate normal distributions. And if I want to classify x sub 0, instead of x, just call x sub 0, if I want to classify x sub 0 into one of these populations, I just simply look at, well, which center is x sub 0 closest to? It's closest to the center corresponding to population 1. So I classify it there. Then building upon then the Mahalanobis distance rule, we have another equivalent way to do this. This is called a posterior probability rule. You might be thinking, well, it would be nice if I could somehow say the probability that x should be in population 1 is 0.9. The probability that x is in population number 2, or should be in population number 2, is, let's say, 0.1. Well, since population 1 had a higher probability, okay, classify into population 1. That's what this posterior probability rule essentially does. Again, suppose that the covariance matrices are equal. And then here's the probability calculation. The probability that x belongs to population I is e to the negative 1/2 d sub I divided by then e to the negative 1/2 d1 plus e to the negative 1/2 d2. Can the numerator ever be larger than the denominator? No. Obviously, you see the numerator is a subset of the denominator. So we get a value between 0 and 1, and we can essentially interpret it as a probability. In the end, though, it's not truly a probability because probabilities are associated with random variables, a random event. We don't necessarily have a random event here. Either the observation is from population 1 or it's from population 2. Either or. We don't necessarily have a random event for that. But we can interpret it as a probability. So again, if, let's say, the probability of population 1 is greater than the probability for population 2, we'll classify the observation to population 1. If it's not, do population 2. And the nice thing, and the reason why people like these posterior probabilities is because it kind of gives you a measure of how sure you are about the classification. If you had probability of 0.51 for population 1, probability of 0.49 for population 2, obviously it shows that you have some uncertainty involved with that particular observation and which population should go into. But if you have 0.99 versus 0.01, well, now you have a lot more certainty. Okay, so far what I've been doing is using mu sub I and sigma sub I. These contain parameters, and obviously in a real life situation you're not going to know what those are, so you're going to need to estimate them. Well, we can estimate them using the same methods that we learned about in the data distributions and correlations section. Estimate them and then use those 4 different methods or those 4 different rules in the same way as I've just described to you, but now using estimated quantities. When sigma 1 is equal to sigma 2, though, well, how do we estimate then one overall covariance matrix? Well, what's usually done is a pooled estimates form. In your first stat course, we talked about hypothesis test for the difference of 2 means. You learn about a pooled variance as a way to try to do the test. Hopefully that sounds familiar. Well, essentially, we now, to come up with a pooled estimate of the covariance matrix, we just extend this same concept to a covariance matrix format, where we are pulling sigma hat 1 and sigma hat 2. We're essentially, in this pool, we are weighting them by the number of observations that one has. Okay, so page 8. As I mentioned earlier, a way to determine, well, what is the best classification method? What is the best prediction method that we're going to use with a particular data set? In order to make that determination, you're going to be very, very focused on what is the overall correct classification percentage. Am I correctly classifying these observations into their corresponding populations 90% of the time? Or maybe just 70% of the time? Maybe just 50% of the time? Which is going to give you the highest correct classification percentage? Or equivalently, which is going to give you the lowest incorrect classification percentage? That's what we're going to be very, very focused on now for the rest of essentially the rest of the semester, is calculating these rates, these percentages. And also that reminds me of one thing that I kind of failed to mention, and that is when we do these methods where we're trying to classify observations into the correct populations, unlike what you've learned in, let's say, in a regression setting, let me find that in the corresponding notes, there's going to be, for us, much less emphasis on interpreting the effect of an independent variable. So I might, for example, I might not really care about, well, what is a quantification of the effect of distance on whether or not a place tick is a success or failure. Rather, all I'm interested in is I want to get it right. I want to get that classification correct. So this is one additional difference between, let's say, regression analysis, where you're often interested in, let's say, interpreting the slope coefficient, your beta hats, versus what we're doing here. So, sorry to digress there a little bit. Okay, so, well, what can happen is that some noise could be put in there, and also in which then might, it can at least a little bit lower your correct classification percentage. It could. It doesn't always. But also, from the standpoint of if you don't need a variable, why waste your time and collect information on it? Okay. But there will be a lot less emphasis, too, on variable selection for what you were basically thinking. A lot less emphasis. Okay, so how can we estimate, then, the correct classification rate, or the incorrect classification rate, too? There's going to be 4 different ways. The most ideal way to do it is to go out and collect some new data. So, for example, with the place ticking data set, I had data from the 1995 season. Well, in order to check how good it works, this method that I can develop based upon this data, how about then I go out and collect data now in the 1996 season? Now, for the 1995 season, it took me 40 hours of entering in the data. Do I really want to spend 40 hours of entering in the data again for the 1996 season? Well, I'm not a graduate student anymore, so no. I make fun of that, but you can see the problem then with collecting new data is that, it could be costly, it could be time-consuming. And so while this is the best way to evaluate how a particular method is going to do is often the most impractical way. So something very similar then is to use what's called a holdout data set. Now if you've had, for example, a full-fledged regression course, you've heard of, let's say, model building and validation data sets, or equivalently some people will call them training data sets versus calibration data sets or test data sets. Essentially what estimates from a holdout data mean is this. And actually I did do this with my place kicking data set. You're going to see this shortly. I actually collected data on about 1,800 observations, 1,800 place kicks. And before I even touched the data to examine, various classification methods, I put aside 400 observations. And then what you've seen so far are the 1,400 observations that I actually built models upon. I build the models on those 1,400 observations, see how it works with that, and then I try this model out on these 400 observations that I kind of set aside. So these 400 observations are kind of serving the role as collecting new data. I didn't actually collect new data, but it's kind of serving that same role. So I'm going to try my methods out on that and calculate how well does it classify. Do I get 90% correct classifications? Do I get 80%? How well? So what's the problem with this method? Well, obviously, now you're not building your statistical method upon as much data as you could. And so you might think that if I'm building a model based upon 1,400 observations versus 1,800, I might not do as well. But fortunately, 1,400 is a pretty sizable number, so I wasn't really worried about that. But let's say instead you're left with a situation, this is what I actually had when I was out in Idaho, it was a time-consuming process to collect this data. And so I basically might have a data set of size 40. Well, do I find my model based upon 30 observations and then put 10 aside? No. Now you're not, you're really, removing a lot of your data, and you don't really have much data to begin with. That's often a question then, or a problem that someone faces. Also, something else to think about here is, if I were to apply a particular statistical method, such as discriminant analysis, to these 1,400 observations, will it do as well in terms of the correct classification rate? Do you think it will do as well with these 1,400 observations as it would with these 400 observations that I put aside? Do you think they would do equally as well, or do you think it would do better in one or the other?
Anything like that should always look better than the original code.
Exactly. If you build a statistical model, or if you come up with a statistical method on some data, you're trying to find the best method for that data. And typically, not always, but typically, that method's going to work best then on that data versus if you were to go out and collect a new data set, or if you were to have a holdout data set. Because it wasn't built upon that extra data. But that's why it's so important to have a holdout data set, or to go out and collect new data so that you can get, let's say, I'm going to use a statistical term here, an unbiased estimate of the correct classification rate. By just applying to your data itself that you built your model or you built your statistical method upon, you are likely to have a biased estimate. Bias up in terms of correct classification rate. Okay, we are out of time. Are there any questions? Okay, that's it for today.